So good day, everyone. Our topic for today is about concurrency, mutual exclusion, and synchronization. So designing correct routines for controlling concurrency activities proved to be one of the most difficult aspects of systems programming. So the ad hoc techniques used by programmers of early multi-programming in real-time systems were always vulnerable to subtle programming errors whose effects could be observed only when certain relatively rare sequences of actions occurred. The errors are particularly difficult to locate since the precise conditions under which they appear are very hard to reproduce. So the learning objectives. So discuss basic concepts related to concurrency such as race conditions, OS concerns, and mutual exclusion requirements. Understand the hardware approaches to supporting mutual exclusion. Define and explain semaphores, monitors, and readers-writers problem. So the central themes of operating system design are all concerned with the management of processes and threads. So includes multi-programming, multiprocessing, and distributed system. So the fundamental to all these areas and fundamental to OS design is concurrency. So concurrency concurrency encompasses a host of design issues, including communication among processes, sharing of and competing of resources such as memory, files, and I/O access, synchronizations of the activities of multiple processes, and allocation of process time to processes. We shall see that these issues arise not just in multiprocessing and distributed processing environment, but even in single processor multi-programming systems. Concurrency arises in three different contexts. Of course, the multiple application, structured applications, and operating system structure. Because of the importance of this topic, there are some, of course, for discussion, for lessons, no? And the appendix focus on concurrency-related issues. Okay, so wherein it discussed the concurrency and multi-programming and multi-processing systems and examine concurrency issues related to distributing processes. With the introduction to the concept of concurrency in the implication of the execution of multiple concurrency processes, we find that the basic requirement of support of concurrent processes is the ability to enforce mutual exclusion. That is, the ability to exclude all other processes from a course of action while one process is granted that ability. Next, we may examine some hardware mechanism that can support mutual exclusion. Then we look at solutions that do not involve busy waiting and that can be supported either by the OS or enforced by language compilers. And we examine three approaches: semaphores, monitors, and message passing. The two classic problems in concurrency are used to illustrate the concept and compare the approaches presented in this lesson. Now, in a single processor, as what we have here, now, this will be the some key terms related to concurrency. So the atomic operations, the critical sections, deadlock, live block, mutual exclusion, race condition, and starvation. So again, in principles of concurrency, in a single processor, multi-programming system process are interleaved in time to yield the appearance of simulation execution, even though actual parallel processing is not achieved, and even though there is a certain amount of overhead involved in switching back and forth between processes. Interleaved execution provide major benefits in processing efficiency and in program structuring. On a multiple processor system, it is possible not only to interleave the execution of multiple processes, but also to overlap them. So at the first glance, it may seem that interleaving and overlapping represent fundamentally different modes of execution and present different problems. In fact, both techniques can be viewed as examples of concurrent processing and both present the same problems. In the case of a uniprocessor, the problems stem from a basic characteristic of multi-programming systems. The relative speed of execution of processes cannot be predicted. It depends on the activities of other processes, the way in which the OS handles interrupts, and the scheduling policies of the operating system. So actually, the difficulties are the sharing of global resources is fraught with peril. No? So again, for example, if two processes both make use of the same global variable, in both perform reads and writes on that variable, then the order in which the various reads and writes are executed is critical. So an example of this problem is shown here in this subsection. So it is difficult for the OS to manage the allocation of resources optimally. So for example, process A may request use of and be granted control of a particular input-output channel and then be suspended before using the channel. It may be undesirable for the OS simply to lock the channel and prevent its use by others' processes. Indeed, this may lead to a deadlock condition. Another is it becomes very difficult to locate a programming error because results are typically not deterministic and reproducible. All of the foregoing difficulties present themselves in a multiprocessor system. As well, because here too the relative speed of execution of processes is unpredictable. A multiprocessor system must also deal with problems arising from the simultaneously execution of multiple processes. Fundamentally, however, the problems are the same as those for uniprocessor system. This should become clear as the discussion proceeds. So this procedure, as what we have here, this will be a simple example of considering the following procedure. And this procedure shows the essential element of a program that will provide a character echo procedure. Input is obtained from a keyboard one keystroke at a time. Each input character is stored in a variable chin, and it is then transferred to variable ch out, no, and sent to the display. Any program can call this procedure repeatedly to accept input user input and display it on the user screen. Now, consider that we have a single processor multi-programming system supporting a single user. The user can jump from one application to another, and each application uses the same keyboard for input and the same screen for output. Because each application needs to use the procedure echo, it makes sense for it to be shared procedure that is loaded into a portion of memory global to all applications. Thus, only a single copy of the echo procedures is used, saving space. So the sharing of main memory among processes is useful to permit efficient and close interaction among processes. However, such sharing can lead to problems, and we may consider the following sequences. Thus, the first character is lost and the second character is displayed twice, as what we have here. No? The essence of this problem is the shared global variable chain, as well a while ago. No multiple processes have access to this variable. If one process updates the global variable and then it is interrupted, another process may alter the variable before the first process can use its value. Suppose, however, that we permit only one process at a time to be in that procedure. Then the foregoing sequence, as what we have here, would result in the following. So this example shows that it is necessary to protect shared global variables and other shared global resources, of course. And that the only way to do that it is to control the code that access the variable. If we impose the discipline that only one process at a time may enter echo, and then once in echo, the procedure must run to completion before it is available for another process, then the type of error just discussed will not occur. However, that discipline may be imposed is a major topic, of course. This problem was stated with the assumptions, and there was a single processor multi-programming OS. The example demonstrates that the problem of occurrency occur when there is a single processor. So in multi-processor system, the same problem of protected shared resources arise, and the same solution works. So first, suppose that there is no mechanism for controlling access to the shared global variable. So this result is that the character input to P1 is lost before being displayed, and the character input in P2 is displayed by both P1 and P2. Again, let us add the capability of enforcing the discipline that only one process at a time may be in echo. Then the following sequence occurs. No? In this case, a uniprocessor system, the reason we have problem is that an interrupt can stop instruction execution anywhere in a process. In the case of multiprocessor system, we have that same condition, and in addition, a problem can be caused because two processes may be executing simultaneously in both trying to access the same global variables. However, the solution to both types of problem is the same: the control access to shared resource. So race condition. A race condition occurs when multiple processor or threads read and write data items so that the final result depends on the order of execution of instructions in the multiple processes. So the operating systems concerns, so what design and management issue are raised by the existence of concurrency? And we can list the following concerns. No? So we need also consider the processor time, memory, files, input, output, usage. And for the process interaction, we can classify the ways in which processes interact on the basis of the degree to which they are aware of each other's existence. So here is the three possible degrees of awareness plus the consequences of each. The processes are unaware of each other. The processes are indirectly aware of each other, and process directly aware of each other. This condition will not always be a clear cut as suggested in this figure. No? Rather, several processes may exhibit aspects of both competitions and cooperations. Nevertheless, it is productive to examine each of the three items in a preceding list separately and determine their implications for the operating system. So we have here the degree of awareness, relationship, influence that one processes and on the other, and potential control problems. Now, competition among processes for resources. Concurrent processes come into conflict with each other when they are competing for the use of the same resource. In its pure form, we can describe the situation as follows. Two or more processes need to access a resource during the course of their execution. Each process is unaware of the existence of other processes, and each is to be unaffected by the execution of the other processes. It follows from this that each process should leave the state of any resource that it is unaffected. Example of resources include input-output devices, memory, processor time, and the clock. There is no exchange of information between the competing processes. However, the execution of one process may affect the behavior of competing processes. In particular, if two processes both wish access to a single resource, then one process will be allocated that resources by the OS and the other will have to wait. Therefore, the process that is denied access will be slowed down. In an extreme case, the block process may never get access to the resource and hence will never terminate unsuccessfully. In the case of competing processes, three control problems must be faced. First is the need for mutual exclusion. Suppose two or more processes require access to a single non-shareable resource such as printer. During the course of the execution, each process will be sending commands to the input-output device, receiving status information, sending data, and or receiving data. We will refer to such as resource as a critical resource. And the portion of the program that uses is a critical section of the program. It is important that only one program at a time be allowed in its critical section. We cannot simply rely on the OS to understand and enforce this restriction because the detailed requirements may not be obvious. So in the case of the printer, for example, we want any individual process to have control of the printer while it prints an entire file. Otherwise, lines from completing processes will be interleaved. The enforcement of mutual exclusion creates two additional control problems. One is that a deadlock. For example, consider two processes P sub 1 and P sub 2 and two resources R1 and R2. Suppose that each process needs access to both resources to perform part of its functions. Then it is possible to have the following situation. The OS assigns R1 to P2 and R2 to P1. Each process is waiting for one of the two resources. Neither will release the resource that it will already owns until it has acquired the other resource and perform the functions requiring both resources. The two processes are deadlocked. So a final control problem is starvation. So the control of competition inevitably involves the OS because it is OS that allocates resources. In addition, the process themselves will need to be able to access the requirement for mutual execution. So in some fashion, such as lacking a resource prior to each issue, and any solutions will involve some support from the OS, such as the provision of the lacking facility. And this figure 5.1 illustrates the mutual exclusion mechanism in abstract term. There are n processes to be executed concurrently. Each process includes one, a critical section that operates on some resource RA, and two, additional code preceding and following the critical section that does not involve access to RA. Because all processes access the same resources RA, is it desired that only one process at a time be in its critical section. To reinforce or to enforce mutual exclusion, two functions are provided: the intercritical and exit critical. So each function takes as an argument the name of the resource that is the subject of competition. Any process that attempts to enter its critical section while another process is in its critical section for the same resource is made to wait. So it remains to examine specific mechanisms to providing the functions intercritical and exit critical. So for the moment, we defer the issue while we consider the other cases of process interaction. Now, the cooperation among processes by sharing. The case of cooperation by sharing covers processes that interact with other processes without being explicitly aware of them. For example, multi-processes may have access to shared variables or to shared files or databases. Processes may use and update the shared data without reference to other processes, but know that other processes may have access to the same data. Thus, the processes must cooperate to ensure that the data they shared are properly managed. The control mechanism must ensure the integrity of the shared data. Because data are held on resources like devices and memory, The control problems of mutual exclusion, deadlock, and starvation are again present. So the only difference is that data items may be accessed in two different modes, reading and writing, and only writing operation must be mutually exclusive. So the cooperation among processes by communication. In the first two cases that we have discussed, each process has its own isolated environment that does not include the other processes. The interaction among processes are indirect. So in both cases, there is sharing. So in the case of competition, they are sharing resources without being aware of the other processes. In the second case, they are sharing values, and although each process is not explicitly aware of the other processes, it is aware of the need to maintain data integrity. So when processes cooperate by communication, however, the various processes participate in a common effort that links all of the processes. The communication provides a way to synchronize or coordinate the various activities. And typically, communication can be characterized as consisting of messages of some sort. Primitives for sending and receiving messages may be provided as part of the programming language or provided by the OS kernel. Because nothing is shared being processed in the act of passing messages, mutual exclusion is not a control requirement for this sort of cooperation. However, the problems of deadlock and starvation are still present. So as an example of deadlock, two processes may be blocked, each waiting for a communication from the other. So an example of starvation, consider three processes, the P1, P2, and P3, that exhibit the following behavior. P1 is repeatedly attempting to communicate with either P2 or P3, and P2 and P3 are both attempting to communicate with P1. So a sequence could arise in which P1 and P2 exchange information repeatedly, while P3 is blocked waiting for a communication from P1. And there is no deadlock because P1 remains active, but P3 is starved. So this will be the requirement for mutual exclusion. So any facility or capability that is to provide support for mutual exclusion should meet the following requirements. And there are a number of ways in which the requirements for mutual exclusion can be satisfied. One approach is to leave the responsibility with the processes that wish to execute concurrently. Processes, whether they are system programs or application programs, would be required to coordinate with one another to enforce mutual exclusion with no support from the programming language or the OS. So we can refer to this as software approaches. Although this approach is prone to high processing overhead and bugs, it is nevertheless useful to examine such approaches to gain a better understanding of the complexity of concurrent processing. A second approach involves the use of special purpose machine instruction, and these have the advantage of reducing overhead, but nevertheless will be shown to be unattractive as general purpose solution. A third approach is to provide some level of support within the OS or the programming language, and there are most important such approaches are examined. Interrupt disabling. In a uniprocessor system, concurrent processes cannot have overlap execution. They can only be interleaved. So furthermore, a process will continue to run until it invokes an OS service or until it is interrupted. Therefore, to guarantee mutual exclusion, it is sufficient to prevent a process from being interrupted. This capability can be provided in the form of primitives defined by the OS kernel for disabling and enabling interrupts. Because the critical section cannot be interrupted, mutual exclusion is guaranteed. The price of this approach, however, is high. The efficiency of execution could be noticeably degraded because the processor is limited in its ability to interleave processes. Another problem is that this approach will not work in a multiprocessor architecture. So when the computer includes more than one processor, it is possible or typical for more than one process to be executing at a time. In this case, disabled interrupts do not guarantee mutual exclusion. So, special machine instruction. In a multiprocessor configuration, several processors shared access to a common main memory. So in this case, there is not a master or slave relationship. Rather, the processor behave independently in a pair relationship, and there is no interrupt mechanism between processor on which mutual exclusion can be based. At the hardware level, as was mentioned, access to a memory location exclude any other access to the same location. With this as a foundation, processor designers have proposed several machines instructions that carry out two actions atomically, such as reading and writing as reading and testing of a single memory locations with one instruction fixed cycle. During execution of the instruction, access to the memory location is blocked for any other instruction referencing that locations. So this will be the compare and shop instruction as what we have here. The compare and shop instruction, also called a compare and exchange instruction. So the version of the instruction check the memory location against a test value. So if the memory location current value is test val, it is replaced with new val. Otherwise, it's left unchanged. So the old memory value is always returned, thus the memory location has been updated if the return value is the same as the test value. This atomic instruction therefore has two parts. A compare is made between a memory value and test value. If the value are the same, a swap occurs, and the entire compare and swap functions is carried out atomically. That is, it is not subject to interpretations. This figure number 1, the compare and swap instruction, shows a mutual exclusion protocol based on the use of this instruction. So a shared variable bolt, this one, is initialized to 0, as you can see here. The only process that may enter its critical section is one of the pints bolt equal to 0. All other processes attempting to their critical section, to enter in their critical section, go into a busy waiting mode. So the term busy waiting or spin waiting refers to a technique in which a process can do nothing until it gets permission to enter its critical section, but continues to execute an instruction or set of instruction that tests the appropriate variable to gain entrance. When a process leaves its critical section, it resets bolt to 0. So at this point, one and only one of the waiting processes is granted access to its critical section. The choice of process depends on which process happened to execute the compare and swap instruction next. So the instruction exchanges the content of register with that a memory location. So both the Intel A132 architecture and A164 architecture ng Itanium contain the Exchd instruction. So properties of the machine instruction approach. So the use of a special machine instruction to enforce mutual exclusion has a number of advantages, and it's listed here. Again, busy waiting is employed, starvation is possible, and deadlock is possible too. So semaphores. We now turn to OS and programming language mechanisms that are used to provide concurrency. This table summarizes mechanism in common use, and we begin in this section with semaphores. The next two sections discuss monitors and message passing. Okay, now, the first major advance in dealing with the problems of concurrent processors came in 1965, no? That is the DJ treatise. Now, it was concerned with the design of the OS as collection of cooperating sequential processes and with the development of efficiency in reliable mechanism for supporting cooperation. And this mechanism can just as readily be used by the user processes if the processor and OS make the mechanism available. The fundamental principle is this: two or more processes can cooperate by means of simple signals, such as the process can be forced to stop in a specified place until it has received a specific signal. Any complex coordination requirement can be satisfied by the appropriate structure of signal. So for signaling, special variables called semaphores are used. So to transmit a signal via semaphore S, a process executes the primitive sim signal S. To receive a signal via semaphore S, a process executes the primitive sim wait S. And if the corresponding signal has not yet been transmitted, the process is suspended until the transmission takes place. Now, to begin, the semaphore has a 0 or positive value. If the value is positive, that value equals the number of processes that can issue a wait and immediately continue to execute. If the value is 0, either by initialization or because a number of processes equal to the initial semaphore value have issued a wait, the next process to issue a wait is blocked, and the same semaphore value goes negative. Its subsequent wait drives the semaphore value further into minus territory, and the negative value equals the number of processes waiting to unblock, and its signal unblocks one of having processes when the semaphore value is negative. So this figure suggests a more formal definition of the primitives for semaphores. The sim wait and sim signal primitives are assumed to be atomic. So more restricted version known as binary semaphore, and the binary semaphore may only take on the value 0 and 1 can be defined by different three operations. So in principle, it should be easier to implement the binary semaphore. No, it can be shown here, and to contrast the two types of semaphore, the non-binary semaphore is often referred to as either a counting semaphore or a general semaphore. A concept related to the binary semaphore is called mutex. Now, a key difference between the two is that the process that locks the mutex or set the value to 0 must be the one to unlock it from set the value to 0. In contrast, it is possible for one process to lock a binary semaphore and for another to unlock it. So for both counting semaphores and binary semaphores, a key is used to hold processes waiting on the semaphore. So the question arises of the order in which processes are removed from such that key. The fairest removal policy is the first in, first out. The process that has been blocked, the longest is released from the queue first. No? A semaphore whose definition includes this policy is called a strong semaphore. A semaphore that does not specify the order in which processes are removed from the key or the queue is a weak semaphore. So in this figure, actually, no, based on one in the sample of the operation of a strongly semaphore, here process A and B and D are ready, and the semaphore count is 1, indicating that one of the D's result is available. So when A issue a sem wait instruction on a semaphore S, the semaphore decrements to 0, and A can continue to execute subsequently and rejoins the ready key. So the B runs, no, this one. The B runs to move then B runs eventually issues a same wait instruction and is blocked, allowing D to run. When D completes a new result, it issues a sim signal instruction, which allows B to move to the ready queue. D rejoins the ready queue and C begins to run, but it is blocked when it is used the same wait instruction. Similarly, A and B run and are blocked on the semaphore, allowing D to resume execution. So when D has a result, it issues a same signal with transfer C to the ready key. So this one. Later cycle of D will release A and B from the block state. So for the mutual exclusion algorithm discussed in the next subsection, illustrate strong semaphore guarantee freedom from starvation, while weak semaphore do not. We will assume strong semaphores because they are more convenient and because this is the form of semaphore typically provided by operating systems. So this figure as an example of a mutual exclusion. It shows a straightforward solution to the mutual exclusion problem using a semaphore S. No? Consider n processes identified in the array P sub I. No, that's why P sub I. Our integer is I of our data type is integer, no, as what we have here, no. All of which needs access to the same resource. Each process has a critical section used to access the resource. In each process, a sim wait S is executed just before okay. So if the value of S becomes negative, the process is blocked. If the value of is 1, this is decremented to 0 and process immediately enter its critical section. Because S is no longer positive, no other process will be able to enter its critical section. The semaphore is initialized to 0. Thus, the first process that executes a same wait will be able to enter the critical sections immediately, setting the value of S to 0. Any other process attempting to enter the critical section will find it busy and will block, setting the value of S to -1. And any number of processes may attempt entry. Each such unsuccessful attempt results in a further decrement of the value of S. When the process that initially entered its critical section departs, S is incremented and one of the block processes is removed from the queue of block processes associated with the semaphore and put it ready state. So when it is next scheduled by the OS, it may enter the critical section. This figure, based on shows a possible sequence for 3 processes using the mutual exclusion discipline. So in this example, 3 process ABC access a shared resource protected by the semaphore lock. So process A executes same wait because the semaphore was a value of 1 at the time of the same wait operations. A can immediately enter its critical section and the semaphore takes on the value 0. While A is in critical section, both B and C perform a same wait operations and are blocked pending the availability of the semaphore. When A exceeds its critical section and performs sim signal, B, which was the first process in the queue, can now enter its critical section. So the program can equally will handle a requirement that more than one process be allowed in critical section at a time. And this requirement is met simply by initializing the semaphore to the specified value. The producer or consumer problem. We now examine one of the most common problems faced in concurrent processing, the procedure consumer problem. The general statement is this: there are one or more producers generating some type of data like records and characters and placing this in a buffer. So there is a single consumer that is taking items out of the buffer one at a time. The system is to be constrained to prevent the overlap of buffer operations. That is, only one agent may access the buffer at any one time. The problem is to make sure that the procedure won't try to add data into the buffer if it is full, and that the consumer won't try to remove data from an empty buffer. We will look at a number of solutions to this problem to illustrate both the power and the pitfalls of semaphores. To begin, let us assume that the buffer is infinite and consists of a linear array of elements. In abstract term, we can define the producer and consumer functions are as follows. So this figure illustrates the structure of buffer B. No, the procedure, the producer can generate items and store them in a buffer at its own pace. No, each time an index n into the buffer is incremented, the consumer proceeds in a similar fashion, but must make sure that it does not attempt to read from an empty buffer. Hence, the consumer makes sure that the producer has an advance beyond it before proceeding. So let us try to implement the system using binary semaphores. Okay, so this figure in this figure, let us try to implement this system using binary semaphores. So this figure is a first attempt. So rather than deal with the indices in and out, so we can simply keep track of the number of items in the buffer using the integer variable n is equal to, of course, the in equal in and minus out. No, the semaphore S is used to enforce mutual exclusion. The semaphore delayed is used to force the consumer to sim wait if the buffer is empty. And this solution seems rather straightforward. The producer is free to add to the buffer at any time. So it performs sim wait BS before appending in sim signal BS afterward to prevent the consumer or any other producer from accessing the buffer during the append operation. Also, when in the critical section, the producer increments the value of n. So if n is equal to 1, then the buffer was empty just prior to this append. So the producer performs sim signal B or the delay to alert the consumer of this fact. The consumer begins by waiting for the first item to be produced using sim wait B. So it then takes an item and increment n in its critical section. If the producer is able to stay ahead of the consumer, then the consumer will rarely block on the semaphore delay because n will usually be positive. Hence, both producer and consumer run smoothly. So this will be the possible scenario for the program of figure 5.9 a while ago. So a fix for the problem is to introduce an auxiliary variable that can be set in the consumer critical sections. No? So this figure has a careful of the logic should convince you that deadlock can no longer occur. A somewhat cleaner solution can be obtained if general semaphores called counting semaphore are used. No? So at this one. Okay? The variables n is now semaphore. So its value is still equal to the number of items in the buffer. Suppose now that it's in transcribing this program, a mistake is made and the operation semi-signals S and semi-signal N are interchanged. And this would require that the semi-signal N operation be performed in the producer's critical sections without interruption by the user. This would require that the same signal and operation be performed in the producer's critical section without interruption by the consumer or another producer. Would this affect the program? No, because the consumer must wait on both semaphores before proceeding in any case. Now, suppose that the same weight N and same weight S operations are accidentally reversed. This procedure or this produce a serious, indeed a fatal flaw. If the consumer ever enters its critical section when the buffer is empty, then no producer can ever append to the buffer and the system is deadlocked. And this is a good example of the subtlety of semaphores and the difficulty of producing correct design. Finally, let us add a new and realistic restriction to the producer-consumer problem, namely that the buffer is finite or finite. The buffer is created as a circular storage. Then the producer and consumer functions can be expressed as follows. So variable in and out are initialized to 0 and n is the size of the buffer. So this figure shows the solution using general semaphores. The semaphore E has been added to keep track of the number of empty spaces. Another instruction example in the use of semaphore is the barber shop problem. No? So it also includes additional example actually in the problem of race condition when using semaphores. Implementation of semaphores. So as what we mentioned earlier, it is imperative that all sim weight and sim signal operations be implemented as atomic primitives. And one obvious way is to implement them in hardware or firmware. Failing this, a variety of schemes have been suggested. And the essence of the problem is one of mutual exclusion. So one or only one process at a time may manipulate a semaphore with either a sim weight or sim signal operation. Thus, any of the software schemes such as Decker's algorithm or Peterson's algorithm could be used. And this would entail a substantial processing overhead. So, another process actually, or another alternative is to use one of the hardware supported scheme of mutual exclusion. So figure 5.14 shows the use of the compare and swap instruction. In this implementation, the semaphore is against the structure, but now includes a new integer component, is that flag. Admittedly, this involves a form of busy waiting. However, the same weight and the same signal operations are relatively short, so the amount of busy waiting involved should be minor. So for a single processor system, it is possible to inhibit interrupts for the duration of a same weight or same signal operations, as what we have here in the interrupts letter B. Once again, the relatively short duration of this operation means that this approach is reasonable. The monitors. Semaphores provide a primitive yet powerful and flexible tool for enforcing mutual exclusion and for coordinating process. So the monitor is a programming language construct that provides equivalent functionality that to that of semaphores, and that is easier to control. The concept was first formally defined in HOR 74. So the monitor construct has been implemented in a number of programming languages, including Concurrent Pascal, Pascal Plus, Modula 2, 3, and Java. It has also been implemented as a program library, and this allows programmer to put a monitor lock on any object. In particular, for something like a linked list, you may want to lock all linked lists with one lock, or have one lock for each list, or have one lock for each element of each list. A monitor is a software module consisting one or more procedures, an initialization sequence, and local data. The chief characteristic of a monitor are the local data variables are accessible only by the monitor's procedures and not by an external procedure. A process enters the monitor by invoking one of its procedures, and one process may be executing in the monitor at a time. Any other processes that have invoked to monitor are blocked, waiting for the monitor to become available. The first two characteristics are reminiscent of those for objects in object-oriented software. Indeed, an object-oriented OS or programming language can readily implement a monitor as an object with special characteristics. By enforcing the discipline of one process at a time, the monitor is able to provide a mutual exclusion facility. The data variables in the monitor can be accessed by only one process at a time. Thus, a shared data structure can be protected by placing it in a monitor. If the data in a monitor represent some resource, then the monitor provides a mutual exclusion facility for accessing the resource. To be useful for concurrent processing, the monitor must include synchronization tools. For example, suppose a process invokes the monitor and while in the monitor must be blocked until some condition is satisfied. A facility is needed by process may enter it. Later, when the condition is satisfied and the monitor is again available, the process needs to be resumed and allowed to re-enter the monitor at the point of its suspension. A monitor supports synchronization by the use of condition variables that are contained within the monitor and accessible only within the monitor. Condition variables are a special data types in monitor which are operated on by two functions, the C-wait and the C-signal. We need to take note that monitor wait and signal operations are different from those for the semaphore. If a process in a monitor signals and no task is waiting on the conditions of a variable, the signal is lost. So in this figure, it illustrates the structure of a monitor. Although a process can enter the monitor by invoking any of its procedure, we can think of the monitor as having a single entry point that is guarded so that only one process may be in the monitor at a time. Other processes that attempt to enter the monitor join a queue of a process block waiting for monitor availability. So once a process is in the monitor, it may temporarily block itself on condition X by issuing C-wait X. It is then placed in a queue of processes waiting to re-enter the monitor when the condition changes and resume execution at the point in each program following the C-wait X call. If a process that is executing in the monitor detects a change in the condition variable X, it issues C-signal X, which alerts the corresponding condition queue that the condition has changed. So in this figure, it shows a solution using a monitor. So the monitor module bound buffer controls the buffer used to store and retrieve characters. The monitor includes two condition variables. Not full is true when there is room to add at least one character to the buffer, and not empty is true when there is at least one character is in the buffer. So a producer can add characters to the buffer only by means of the procedure append inside the monitor, and the producer does not have direct access to buffer. The procedure first check the condition not full to determine if there is a space available in the buffer. If not, the process executing the monitor is blocked on that condition, and some other process may now enter the monitor. Later, when the buffer is no longer full, the block process may be removed from the queue, reactivate, and resume processing. After placing character in the buffer, the process signals are not empty conditions. So a similar description can be made of the consumer functions. So this time, how about the alternate mode of monitors with notify and broadcast? Hoar's definitions of monitors requires that if there is at least one process in a condition queue, a process from the queue runs immediately when another process issues a C signal for that condition. Thus, the process issuing the C signal must either immediately exit the monitor or be blocked on the monitor. One useful refinement that can be associated with the cnotify primitive is a watchdog timer associated with each condition primitive. A process that has been waiting for the maximum timeout interval will be placed in a ready state regardless of whether the condition has been notified. When activated, the process checks the condition and continues if the condition is satisfied. The timeout prevents the indefinite starvation of process in the event that some other process fails before signaling conditions. So message passing. When processes interacts with one another, two fundamental requirements must be satisfied: synchronization and communication. Processes need to be synchronized to enforce mutual exclusion. Cooperation or cooperating processes may need to exchange information. One approach to providing both of these functions is message passing. Message passing has the further advantage that it lends itself to implementation in distributed system as well as in shared memory, multiprocessor, and uniprocessor system. Message passing system comes in many forms. In this, we provide a general introduction that discusses features typically found in some such system. The actual functions of message passing is normally provided in the form of pair of primitives, either send and receive. So, as what we have here in our figure, our table 5.5. Synchronization. The communication of a message between two processes implies some level of synchronization between the two. The receiver cannot receive a message until it has been sent by another process. In addition, we need to specify what happens to a process after it issues a send or receive primitive. Consider the send primitive first. So when a send primitive is executed in a process, there are two possibilities. Either the sending process is blocked until the message is received, or it is not. Similarly, when a process issues a receive primitive, of course, there are two possibilities. Number one, if a message has previously been sent, the message is received and execution continues. Number 2, if there is no waiting message, then either the process is blocked until a message arrives or the process continues to execute, abandoning the attempt to receive. Thus, both the sender and receiver can be blocking or non-blocking. 3 combinations are common, although any particular system will usually have only 1 or 2 combinations implemented. We have the blocking, send, blocking, receive, non-blocking, send, blocking, receive, and non-blocking, send, non-blocking, receive. Addressing. Clearly, it is necessary to have a way of specifying in the send primitive which process is to receive the message. Similarly, most implementation allow a receiving process to indicate the source of a message to be received. The various schemes for specifying processes is send and receive primitive fall into 2 categories, direct addressing and indirect addressing. With direct addressing, the send primitive includes a specific identifier of the destination process. The receive primitive can be handled in 1 of 2 ways. One possibility is to require that the process explicitly designate a sending process. Thus, the process must know ahead of time from which process a message is expected, and this will often be effective for cooperating concurrent processes. In other cases, however, it is impossible to specify the anticipated source process. An example is a printer server process, which will accept a print request message from any other process. For such application, a more effective approach is the use of implicit addressing. In this case, the source parameter of the received primitive possesses a value return when the receive operation has been performed. The other general approach is indirect addressing. In this case, messages are not sent directly from sender to receiver, but rather are sent to the shared data structure consisting of queues that can temporarily hold messages. Such queues are generally referred to as mailboxes. Thus, for 2 processes to communicate, one process sends a message to the appropriate mailbox, and the other process picks up the message from the mailbox. A strength of the use of indirect addressing is that by decoupling the sender and receiver, it allows for greater flexibility in the use of messages. The relationship between senders and receivers can be one-to-one, many-to-one, one-to-many, or many-to-many, as shown in this figure 5.18. One-to-one relationship allows a private communication link to be set up between 2 processes, and this insulates their interaction from erroneous interference from other processes. Many-to-one relationship is useful for client-server interaction. One process provides service to a number of other processes. In this case, the mailbox is often referred to as a port. A one-to-many relationship allows for one sender and multiple receivers, and it is useful for application where a message or some information is to be broadcast to a set of processes. A many-to-many relationship allows multiple server processes to provide concurrent service to multiple clients. So, a related issue has to do with the ownership of a mailbox. In the case of a port, it is typically owned by and created by the receiving process. Thus, when the process is destroyed, the port is also destroyed. For the general mailbox case, the OS may offer a create a mailbox service. Such mailboxes can be viewed either as being owned by the creating process, in which case they terminate with the process, or as being owned by the OS, in which case an explicit command will be required to destroy the mailbox. So a message format, no? The format of the message depends on the objective of the messaging facility and whether the facility runs on a single computer or in a distributed system. So for some operating system, designers have preferred short fixed-length messages to minimize processing and storage overhead. If a large amount of data is to be passed, the data can be placed in a file and the message then simply reference that file. So a more flexible approach is to allow variable length messages. In this figure, it shows a typical message format for operating systems that support variable length messages. The message is divided into two parts, a header which contains information about the message and a body which contains the actual contents of the message. The header may contain an identification of a source and intended destination of the message, a length field and a type field to discriminate among various type of messages, and there may be also additional control informations such as pointer field so that the linked list of messages can be created, a sequence number to keep track of the number and order of messages passed between source and destination, and a priority field. So keying or queuing discipline. The simplest queuing discipline is first in, first out, but this may not be sufficient if some messages are more urgent than others. An alternative is to allow the specifying of message priority on the basis of message type or by designation by the sender. Another alternative is to allow the receiver to inspect the message queue and select which message to receive next. So the mutual exclusion in this figure shows one way in which message passing can be used to enforce mutual exclusion. No? We assume the use of the blocking receive primitive and the non-blocking send primitive. A set of concurrent process shared a mailbox and box which can be used by process to send and receive. The mailbox is initialized to contain a single message with null content. So a process wishing to enter its critical section first attempt to receive messages. If the mailbox is empty, then the process is blocked. Once a process has acquired the message, it performs its critical section and then places the message back into the mailbox. Thus, the message function as token that is passed from process to process. And the preceding solution assumes that if more than one process performs the receive operations concurrently, then if there's a message, it delivers to only one process and the others are blocked. Or if the message queue is empty, all the processes are blocked. When a message is available, only one block process is activated and given a message. So this figure is a solution to the bounded buffer procedure, a producer consumer a problem using a basic mutual exclusion power of message passing. So the problem could have been solved with the algorithmic structure similar to as presented a while ago in figure 5.13. Instead, the program takes advantage of its ability of message passing to be used to pass data in addition to signals. Now, two mailboxes are used. As producer generates data, it is sent at messages to the mailbox may consume. As long as there is at least one message in the mailbox, the consumer can consume. Hence, may consume serve as the buffer. The data in the buffer are organized as a key. And the size of the buffer is determined by the global variable capacity. Initially, the mailbox may produce is filled with a number of null messages equal to the capacity of the buffer. The number of messages in my produce shrink with each production and grows with each consumption. And this approach is quite flexible. There may be multiple procedure or producers and consumers as long as all have access to both mailboxes. The system may even be distributed with all producer processes and the may produce mailbox at one side and all the consumer process and the may consume mailbox to another. So, readers, writers problem. in dealing with the design of the synchronization and concurrency mechanism, it is useful to be able to relate the problem at hand to no problem and to be able to test any solution in terms of its ability to solve these known problems. In the literature, several problems have assumed importance and appear frequently both because they are example of common design problems and because of their educational value. One such problem is the producer's consumer problem, which has already been explored. So the reader's writer problem is defined as follows. There is a data area shared among a number of processes. The data area could be a file, a block of main memory, or even a bank of processor registers. There are a number of processors or processes that only read the data area and the number that only write to the data area. And the condition must be satisfied if any number of readers may simultaneously read the file. Only one writer at a time may write to the file, and if a writer is writing to the file, no reader may read edit. Thus, readers are processes that are not required to exclude one another, and writers are processes that are required to exclude all other processes, readers and writers alike. So readers have priority. As what we have here in figure 5.22 is a solution using semaphores showing one instance each of a reader and a writer. The solution does not change for multiple readers and writers, and the writer process is simple. The semaphore WSEM is used to enforce mutual exclusion. As long as writer is accessing the shared data area, no other writers and no readers may access it. The reader process also makes use of WSEM to enforce mutual exclusion. However, to allow multiple readers, we require that when there are no readers reading, the first reader that attempts to read should wait on WSEM. So when there is already at least one reader reading, subsequent readers need not to wait before entering. So the global variable read count is used to keep track of the number of readers, and the semaphore X is used to assure that read count is updated properly. Writers have a priority. In the previous solution, readers have priority. Once a single reader has begun to access the data area, it is possible for readers to retain control of the data areas as long as there is at least one reader in the act of reading. Therefore, writers are subject to starvation. This figure shows a solution that guarantees that no new readers are allowed access to the data area once at least one writer has declared a desire or right. So, for writers, the following semaphores and variables are added to the ones already defined. So, in this area, as what I mentioned, a semaphore RSEM that inhibits all readers while there is at least one writer defined. So, a semaphore RSEM that inhibits all readers while at least one writer desiring access to the data area. A variable write count that controls the setting of RSEM, and a semaphore Y that controls the updating of write count. So for readers, one additional semaphore is needed. A long queue must not be allowed to build up on RSEM. Otherwise, writers will not be able to jump the queue. Therefore, only one reader is allowed to queue on RSEM with any additional readers queuing on semaphore Z immediately before waiting on RSEM. In this table, summarize the possibilities. An alternative solution which gives writers priority and which is implemented using message passing. In this case, there is a controller process that has access to the shared data area. Other processes wishing to access the data area send a request message to the controller, are granted access with an OK reply message, and indicate completion of access with a finished message. The controller is equipped with 3 mailboxes, one for each type of message that it may receive. The controller process services write request messages before request message to give writers priority. In addition, mutual exclusion must be enforced. To do this, the variable count is used, which is initialized to some number greater than the maximum possible number of readers. In this example, we use a value of 100, and the action of the controller can summarize as if count greater than 0, then no writer is waiting and there may or may not be readers active. Service all finished message first to clear active readers, then service write request, and then read request. If count is equal to 0, then only request outstanding is write request. Allow the writer to proceed and wait for a finished message. If count is less than to 0, then a writer has made a request and it is being made to wait to clear all active readers. Therefore, only finished messages should be serviced. So to summarize, the central themes of modern operating system are multi-programming, multi-processing, and distributed processing. Fundamental to these themes and fundamental to the technology of OS design is concurrency. So when multiple processes are executing concurrently, either actually in the case of the multiprocessor systems or virtually in the case of a single processor, multi-programming system, issues of conflict resolution and cooperation arise. Concurrent process may interact in a number of ways. Processes that are unaware of each other may nevertheless compete for resources, such as processor time or access to input-output devices. Processes may be indirectly aware of one another because they share access to the common object, such as block of main memory or a file. And finally, processes may be directly aware of each other and cooperate by the exchange of information. The key issues that arise in this interaction are mutual exclusion and deadlock. So, mutual exclusion is a condition in which there is a set of concurrent processes, only one of which is able to access a given resource or perform a given functions at any time. Mutual exclusion techniques can be used to resolve conflicts such as competitions for resources and to synchronize processes so that they can cooperate. An example of the latter is the producer's consumer model, in which one process is putting data into a buffer and one or more processes are extracting data from the buffer. One approach to supporting mutual exclusion involves the use of a special purpose machine instruction. And this approach reduces overhead but is still inefficient because it uses busy waiting. Another approach to supporting mutual exclusion is to provide features within the OS. Two of the most common techniques are semaphores and message facilities. Semaphores are used to signaling among processes and can be readily used to enforce a mutual exclusion discipline. Messages are useful for the enforcement of mutual exclusion and also provide an effective means of inter-process communications. And that's it for that topic.